some previous video, I stated a result about convergence of subRiemannian distances when one has convergence of the subRiemannian structures. I haven't discussed yet the reasons why that result is true. We will do it later. I will now present one more application, the third one, of this result. This application is Mitchell's theorem, which characterizes the tangents of subRiemannian manifolds at equiregular points. Let's see this application. I'm going to present more consequences of the results that if you have polarizations converging to a limiting polarization with norms converging to a limiting norm, then, and the limiting polarization is bracket generating, then the Kernel-Theodorist distances associated to lambda converge uniformly on compact sets to 0. So this is a theorem that we stated, we haven't proved yet, but now I'm going to present some consequences. And the consequence that I'm going to present is the third one. We already present two of them, and it's Mitchell's theorem. It's a theorem that characterizes tangent spaces of Kernel-Theodori, tangent spaces of Kernel-Theodori spaces. So suppose we have a manifold, polarization, and a norm. So this is a Kernel-Theodori space. So the subbundle is of the tangent bundle is bracket generating. We fix a point in M, and then we consider vector fields that are a frame. This is a frame for delta around P. Okay, so now because the subbundle delta is assumed bracket generating, what we can do, we can perform brackets of these vector fields, and we know that if we can consider enough iterated brackets, we will find a frame for the whole tangent bundle of the manifold M. So let's choose some of these brackets. So for example, among the brackets xi, xj, we can choose some of them so that together with the vector fields x1, xm, they form a frame for the bundle delta 2, which I recall you that delta 2 at the point P is just is delta P together with all the bracket xy at P, such that x and y are sections of delta, namely they're horizontal vector fields. Okay, so we choose some vectors that they vector fields that form a frame for 42, and then we continue. So we continue, and then we have a frame of delta 3, delta 4, and so on. So what we get this frame. At the end, step S is going to be a frame for the whole tangent bundle, a frame for Tm, made of commutators of the original frame of the subbundle. So we have x1, xm was the frame for delta. then let's say m1 plus m plus 1 up to x m2 m2. So this is also say m1, and now this one are a frame for delta 2, and so on. Plus 1 up to xms. Okay. Now that we have this frame, we can consider exponential coordinates with respect to this frame. So now we consider coordinates as follows. So they're going to be centered. So remember that we fix a point P in M, around which we took the horizontal frame. And then we are going to have coordinates that are centered at P. So namely 0 is going to be sent to P. So U is some open subset of Rn, and every point, say T, n equal T, is going to be mapped to M in the following way. So you start with P, and then you flow per time T1, first coordinate of T, along the vector field X1. And then you flow again, you iterate flows X n, the last one, Tn. So that say that this number was n. Okay, so these are flows. Okay. So iterating this flow, we get a map, and it's easy to prove that since these vector fields form a frame, then this map on some open set around 0, so 0 is sent to P, and in the neighborhood of 0, this map is really a diffeomorphism. Because some partial derivative are exactly these vectors that are a basis of the tangent at P. Okay, so we have coordinates. Now, in these coordinates, now we are going to put a group structure, and we will show that in these coordinates, the distribution, the dilated distribution, will converge to a limiting distribution, and this is going to be the tangent of the subRiemannian manifold at P. Okay, so slowly, so let's define some things. So for example, these coordinates. So in these coordinates, namely in this Rn, so let's define v1 to be just the delta at 0, right? So delta at the point at 0, and then which is the same of the span of x1 at 0. Remember, now 0 and P, they are identified. Okay, so 0 is sent to P. 6 and up 0. And we also define Vj. Similarly, this was the span of the vectors that we had to add to define delta j. So this was delta mj plus 1. So and j minus 1 plus 1 dot evaluated at 0 dot xmj at 0. Okay, so what we have defined, we wrote Rn as the direct sum of V1 Vs. S was the step. Okay, now in these coordinates we have the splitting. We define some dilations, which are just a linear map. See, so define for all lambda the map delta lambda that goes from Rn to Rn is the linear map such that the map restricted to Vj is the multiplication by j. on Vj, by lambda to Vj. Okay, so these are maps in coordinates. At a priori, at the moment on our end, there is no group structure. Okay, so these are just maps. Okay, eventually we'll put a group structure for which these maps are going to be automorphisms, and the group structure is not the sum in general. Okay, so the first fact that I'm going to claim and without proof, and is the fact that taking the dilation of vector fields, horizontal vector fields, will converge. Namely, this is the fact. So, if you there exists the following limit. So you take xi. So this was for all I from 1 to m. So the horizontal vector field that we fixed. You consider it, and now you dilate it by lambda. And then this is scalar multiplication, and then you dilate with the map. So you consider the push forward by delta minus 1. So this map here, so the map is linear, so it's the same of the push. So this is the push forward. So is the map applied to vector fields? Okay, this is the linear map, so it's the same map itself, if you prefer. Okay, now the claim is that this limit, as lambda goes to 0, exists. So let's call it xi hat, or maybe xi 0, right? Right? Yeah, let's okay. So this limit exists, and another claim I will explain better. So x0 up to xm0, they are still bracket generating. What you should think is that this vector here, this vector field, this we can call it x lambda I. Of course, this is up to a change of coordinates. These are just the same vector fields dilated by lambda. Now, what I'm claiming is that these are bracket generating, and because we dilated, it's clear that they are defining the dilation of the subRiemannian structure. And now the claim of this fact is that these vector fields converge to some vector field, okay, which is still bracket generating. And therefore it's going to be clear that the subRiemannian structure defined by these dilated vector fields will converge to the one of the limiting one, because of this theorem that we are considering, and now we are considering consequence of this fact. Okay. Actually, for a better understanding of why these limiting vector fields will form a stratification, let me state an even stronger fact. So now I'm going to consider not just the first group of vectors, of vector fields, but all of them. So we have S groups, the first one up to the S, and for all I, so now they go from M j minus 1 up to plus 1 up to mj, right? So this is the indices of degree I, the indices of degree j. So if we fix such an I, so what we have is that the vector of xi is a section of the jth bundle, but not a section of the previous one. Then what we could do, we can dilate these vectors, but now we take a power j, and now we push them forward. And I claim that also this limit exists as lambda goes to 0. And so let's call this limit x at 0 I. So these are vector fields in Rn. So, and again, this is a sequence of vectors. So let's call it x lambda I. And really these vectors converge. But now we for j also greater than 1, we had to weight them in a different way. However, still look what's happening at 0. At 0, okay. So this map is the dilation, right? And so and fix the origin, right? And this is at the origin. This is a vector at the origin, and the coordinate along I is exactly dilated by delta j. This is how delta j is performed. So which means that what we have is that this vector field x I lambda at 0, they all coincide to del xi, the initial xi at 0. So these vectors, at least at 0, they don't blow. Actually, they stay some basis. So it's maybe this is a little bit of understanding why this is not, at least it's not blowing this sequence of vector fields. Now let's see what happens when we bracket them. So let's say that we have a bracket of two vector fields. Right? Say that this gives another vector field in our list. Okay, let's say that let's look at the degrees. So let's say that this is, let's call the degree dj, right? Namely, in with this languages, I was having degree j, right? So each of them comes in the group. So let's say that these are three vectors of degree di, dj, and dk. Now, because of the construction, what we have is that dk is the sum of di plus dj. So, in other words, if this is formed by di many commutators, this is formed by dj many commutators, this is formed by di plus dj commutators. This is what I'm saying. Okay, now what happens now if we perform this dilation? Okay, so the push forward commutes with a bracket, delta lambda star xi, delta lambda star xj. Now let's multiply. Now I'm going to multiply by lambda di plus dj to this power here, lambda star x lambda. Remember that, so this is a linear map, so I can put this one here or there, is the same. Okay, so this is the vector that I would consider, okay, for taking this limit. But now I can put delta di in front of delta lambda star xi, and the other lambda dj in front of delta lambda star xj. And then passing to the limit, what we get is that xk0 is equal to xi0 xj0. So we have the same form of bracket for the basis vectors, for the vectors that we choose in the limit. Okay. But now what happens instead if we take two vectors in J and they don't form an element in the basis? Actually, what happens if they belong to a lower degree space of vector fields? So what if we bracket xi with xj, this is a section of delta I plus j minus 1, so the previous one. Then the same formula will show that xi lambda, xj lambda, actually this will go to 0. And therefore what we have realized is that the composition of bundles that we had at the beginning, I, v, j, is contained in vi plus j. And moreover, vi, so now this is defined into, this is now I see it as a frame, so as a distribution generated by the vector fields in the frame. So in other words, these vector fields will, or the limiting one, they will span, they define a subbundle which they be called V1. This one, they will define a subbundle that we call V2, and so on, V3. And at the origin, they're exactly this one. But now we have at every point, now we really have a subbundle, okay? Okay, so what we have done, we don't have a group structure, but what we have is a stratification of vector fields. So x1, 0, xm, 0, they Lie span, and the algebra they Lie span is finite dimensional and it's nilpotent and satisfy this condition here. So they Lie span a nilpotent Lie algebra for which they span, now this is as a sum, the first layer of a stratification. I will now discuss a more general construction of how one can get a stratified Lie algebra from a filtration. So the fact that the tangent of a subRiemannian manifold is a kernel group, it comes from a construction that is much more general than in that situation. So I will now present this construction, which is called the Nilpotentization, and then I will state the stronger statement of Mitchell's theorem. Okay, so so suppose now we have M, a manifold, smooth manifold, and then we have the space of smooth vector fields on M. And then suppose we have a family of vector spaces. So let's call it D1 contained in D2, so on, up to DS, which is the whole space of vector fields on M. So, and let's assume, so these DIs are just vector subspaces, okay? Something, an increasing union like this is called a flag, okay? But now we are having a flag with one more property, such that, so now we can perform brackets, okay? So if you take a bracket in the ith element or ith space and I bracket with an element in the j space, I assume that this is inside the di plus j. So such a family like this is called a filtration. So one such a family is called filtration. Of course, the example that we have in mind is the vector, the filtration generated by a bracket generating subbundle. So if we have a subbundle, Tm, so this is, suppose this is a bracket generating subbundle, then we can define D1 to be just the the sections of delta, namely the smooth vector fields tangents to delta, and we define delta I recursively as, so the I plus 1 as di plus all the elements that you get as sections of delta bracket di. In other words, these are brackets of less or equal than I plus many vector fields. Okay, so this is, so I say, brackets of I plus 1 or less vector fields tangent to delta. Okay, so this is the example that we should keep in mind. Okay, but in general, suppose you have a filtration. So for the I from 1 to S filtration of the space of vector fields on a manifold, we define the associated graded algebra it should be Lie algebra is the setwise. This is the direct sum of the quotients di mod out di minus 1. So in other words, it's the first one is just d1, and then is d2 mod d1, and the last one is ds mod ds minus 1. Okay, this is setwise as a vector space with bracket such that, so suppose you have x an element in the I and an element in the j, then remember, from the fact that we have a filtration, this tells us that x bracket y is in the I plus j. This is by definition of filtration. Now we will define the bracket between x plus the I plus I minus 1, y plus the j minus 1. And you see, this is these are exactly two vectors that are in sum of this vector space in this direct sum. Okay, and then we will extend the vector space, the Lie bracket linearly. Okay, so I'm defining the bracket on this space, just defining to be linear, and I'm defining on each of the spaces. Okay, so this is by definition is the bracket of x, y plus di plus j minus 1. Okay, so this element is in di plus j, so we can think this is an element of di plus j modulo di plus j minus 1. So it is an element in the Lie algebra, and one can check that this is really well defined in the sense that, of course, because again of the filtration, I have really defined an element, a bracket of these subspaces. All right, and so this is a definition, and what one should immediately realize is that this remark that now this becomes a Lie algebra, D2 mod D1 this direct sum gives a grading. Okay, maybe I didn't say. One should observe that this is a Lie bracket on this Lie algebra, and this direct sum decomposition is a grading. So what we get is a graded Lie algebra, but one should also notice that in the case that we were interested, so where D1 is the section of delta, and we have all others. So di plus 1 is di plus section of delta di. In this case, we have that D1 really Lie span, because the way it's defined, the algebra, the Lie algebra that we define in here. Okay. So it's a graded algebra with the first layer that is Lie generating, and therefore, hence, we get a stratification. Okay, so this is very close to be the tangent of the subRiemannian manifold that we want. But now we have to fix a point. Okay, so I'm ready to state the general theorem of Mitchell. So let m delta norm be equiregular subRiemannian or subFinsler manifold with the distance d, with the Carnot-Theodori distance d. Fix a point P in M. Then the tangent cone of MD at P exist, and it is the following Kernel group. So it's a kernel group, and I'm going to describe it for you now, what it is. So one take D1, the section of delta, and again di plus 1 is the section of delta bracket with di plus di. And then what one does is the following. So V1 is going to be these vector fields evaluated at P, which of course is nothing else than the subbundle at P. Okay, but the other layers Vj, they're going to be the quotient of di at P modulo di minus 1 at P. It's like the Nilpotentization. Maybe I didn't say that. So this Lie algebra is called the Nilpotentization of the filtration. Okay, so now it's like similar to the Nilpotentization of this family, but now we evaluate at P. Okay, it's important that we first consider the Nilpotentization of the whole family of vector fields, because here we have defined the Lie bracket. Okay, now that we have defined the Lie bracket, this will induce a Lie bracket on the direct sum of these spaces. Okay, so the bracket, Lie bracket, on the nilpotentization sum of di modulo di minus 1 induces a bracket on this V1 Vs. So this V1 Vs is a finite dimensional, so it's a finite dimensional Carnot algebra or stratified algebra. So stratified Lie algebra. Now the claim is that the Kernel group G, the tangent at P, is the only Kernel group with Lie algebra V1 Vs. Okay, this was what I wanted to say about Mitchell's theorem. I will conclude these discussions on Mitchell's theorem on stating a generalization of Pansus' version of Rademaker theorem. So, generalization of Pansus' version of Rademaker theorem. Actually, this theorem is due to Margulis, the Fields medalist, and Mostov. Is the following. Suppose you have M1 and M2 equiregular Carnot-Carat-Theodori spaces. Okay? So, sub-Finsler manifold or subRiemannian manifolds, but equiregular. So what we know that at every point we have a tangent, and this tangent is a Kernel group. Okay? Now suppose we have F, a map from M1 to M2, that is Lipschitz. Then the conclusion, the statement of the theorem is that at almost every point and this almost every point is with respect to any volume measure, volume form, or if you want in coordinate, it's the Lebesgue measure. F is, let me put in quote, is intrinsically differentiable when intrinsically differentiable, we'll also say that the intrinsic differential is a group morphism. Say, and the intrinsic differential is a Carnot morphism between Kernel groups. Let me explain better this statement. So what's the meaning? Since we have the convergence toward the Kernel group is clear in coordinates, in exponential coordinates, it's better to use them because we really have convergence on compact sets. So in exponential coordinates, with respect to an adapted frame, with respect to an adapted frame, which means that where then we have the dilations give us the structure of a Kernel group. As say h goes to 0, then delta h minus 1 compose f compose H. So let's say that these are coordinates, so these are centered in a point P in the domain and f of P in the target. Then see these are the dilation at P, these are the dilation at f of P. Now this sequence of maps, now they're defined in Rn, these maps converge uniformly on compact sets to Lie group morphism, homomorphism, Lie group homomorphism of the tangent cones, which are kernel groups. And in particular, these maps are also dilation invariant. Okay. Last thing, a consequence. Here's a very simple consequence. The only subRiemannian manifolds that can be biLipschitz embedded into some Euclidean space are the Riemannian ones. Namely, when the subbundle is all the tangent bundle, then we have a Riemannian manifold. Okay, well, this is an immediate consequence. I'll just repeat. Suppose you have subRiemannian manifold that embeds into Euclidean space via biLipschitz map. Now, the Lipschitz map by Margulis Mosto is differentiable almost everywhere. One can differentiate and get still a biLipschitz map from the tangent space, any tangent space where the map is differentiable, to Rn. Now, unless the map is unless the manifold is Riemannian, the kernel group is not abelian, because one should observe that the tangent kernel group has the same rank than the initial manifold. So if one starts with a manifold whose and a subbundle whose rank is strictly smaller than the rank of the tangent bundle, then the same thing will happen for the tangent kernel group, because you see the topological dimension stays the same and the rank stays the same of the horizontal bundle. Okay, so which means that if the subRiemannian manifold is not Riemannian, then the tangent, every tangent at every point, is not going to be an abelian kernel group. Okay, but we know that the only kernel groups that can be embedded via an injective isomorphism into Euclidean space are the Euclidean, the abelian ones. Okay, good. So, and this gives tells us that a proper subRiemannian manifold is not embeddable. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.